Hello, this is IoT Security and Privacy, lightweight cryptographic protocol tailored for resource-constrained IoT devices by Richard, Christopher, Morgan, and Miguel. The Internet of Things is expanding rapidly into various aspects of daily life, and securing IoT devices is challenging due to their limited computational power and storage, making lightweight cryptography the only viable solution for balancing performance and security. The questions we aim to answer include: how does lightweight cryptography compare in terms of efficiency and battery consumption in IoT devices? How resilient are lightweight cryptographic protocols to common and emerging attacks? What are the trade-offs between performance and security when implementing lightweight cryptography? And can symmetric and asymmetric cryptographic techniques be optimized for IoT environments? For the first question, we tested LWCs in two ways while measuring for performance metrics. First, IoT hardware on the two common platforms, ESP32 and Arduino, then across three different wireless communications, Wi-Fi, Bluetooth low energy, and low energy, simulating sensors, smart lights, and wearables. We tested ChaCha20, Spec, and Ascon as our LWCs. To keep things consistent and standards compliant, we didn't modify the key sizes or use custom versions. For questions 2 and 3, we had to integrate outside research with our collected data to interpret the trade-offs our tested LWCs had between performance metrics and security. Question 4, we added RSA, AES, and ECC to our analysis, measuring the same performance metrics. Oakley Hardware Simulator was capable of simulating ESP32 and Arduino hardware platforms, with templates and built-in functions for easy testing and data collection. Python and PyCryptodome library gave us the opportunity to collect those same metrics, but simulating different types of devices across different types of wireless communications, an important aspect of IoT. Different modules and libraries were used for both these tools to aid collection, and published research was integrated as well. We started our hardware test on the common IoT hardware ESP32. These graphs display the encryption and decryption speeds in milliseconds on the x-axis, and power consumption in megajoules on the y-axis. For the LWC algorithms, ChaCha20 in blue, Spec128 in green, and Ascon128 in orange. We continued our data collection on IoT hardware, repeating the process on Arduino Mega, another common piece of IoT hardware and the most comparable version to ESP32 that Woke could simulate, recording those same metrics. What we found was that Ascon was the best performing LWC for the hardware we tested. It had both the fastest encryption and decryption for both platforms and the lowest energy consumption. On the other end, Spec was the worst performing, being only slightly faster and less energy consuming for encryption, but considerably slower and more energy consuming for decryption, when compared to ChaCha, which is more security focused. Algorithms also use less energy to encrypt on Arduino than on ESP, and less energy to decrypt on ESP than Arduino. But this could be due to the simplicity of the task and may not hold for more complex functions of IoT devices. Which one should be chosen should be based on the amount of power consumption and devices needed to perform its specified tasks versus how much would be left for cryptography, also taking into account the security needed in the common attacks against the device.
Hello, this is Morgan, and this is my portion of our presentation. This chart shows the average encryption performance of each algorithm across these protocols: Wi-Fi, Bluetooth Low Energy, and Long Range, and three environments: line of sight, urban, and fading. Line of sight is a direct clear connection. Urban introduces interference from obstacles like buildings. Fading simulates motion, causing fluctuations. In this test, we only measured energy used by cryptographic operations, not CPU or wireless transmission. In general, taller bars mean higher time and energy usage, which is less ideal for battery powered devices. This chart uses the same structure, but now focuses on the decryption performance. As before, taller bars mean more average or time spent. A key trend here is that fading environments tend to increase both metrics, especially for protocols not optimized for interference or mobility. This graph compares the average energy consumption of each algorithm based on its key strength. The x-axis shows the key size. Spec and Ascon used 128-bit keys, while ChaCha20 used its standard 256-bit key. The y-axis shows the average energy needed to encrypt a single message in millijoules. Despite the higher key size, ChaCha20 was the most energy efficient. Spec landed in the middle, while Ascon, although secure in NISPAC, used the most energy in this setup. As a reminder, our energy measurements in my section reflect only the cryptographic operations. In this setup, ChaCha20 clearly stood out, delivering the fastest times, lowest energy consumption, and longest battery life. It's a strong candidate for wearables and high throughput IoT applications, where speed and efficiency matter most. SPEC held a balanced position, offering moderate security and decent efficiency. Ascon, while secure and standardized, consistently used more energy and had slower performance. In energy constrained or high frequency use cases, it may not be the best fit, at least in this kind of stripped down test environment.
This is Richard Aldrich. My section was on asymmetric versus symmetric algorithms. We started off by comparing the two. So we have ECC and RSA against our chosen lightweight cryptography methods. And as you can see across the board, ECC and RSA are heavier. Our findings suggested that a hybrid model was the best practice for IoT devices. And we'll get to these findings later, but just to show that we wrote a script and we used RSA for secure key exchange and AES for fast and efficient encryption. Regarding symmetric versus asymmetric, we found that symmetric encryptions like ChaCha20 and Present outperformed asymmetric methods significantly. In fact, these symmetric algorithms were 10 to 70 times faster than RSA, used up to 200 times less energy, and had much smaller memory footprints. AES, while slightly slower, showed minimal performance variability, making it ideal for predictable workloads. RSA, on the other hand, was resource heavy and slow, less than ideal for IoT devices with limited power and processing capability. In terms of energy encryption speed, energy use, and security strength, Ascon 120 emerged as the best overall performer, being both fast and energy efficient. ChaCha20 also stood out for offering a strong balance, particularly for always-on sensors due to its low energy draw and moderate CPU usage. SPEC, while lightweight, lagged behind in both speed and security strength. Finally, is our findings on our hybrid model. We used AES for encryption and RSA for key exchange. Our findings showed that efficient data encryption faster than asymmetric alone, but slower than symmetric only. The lowest energy consumption compared to any of the other encrypted methods we tested. And it gives IoT devices security that symmetric methods cannot. These findings are consistent with our research, especially found by Henriques and Wernicke. Thank you.
Hello, I'm Miguel Sanchez, and I'm doing my part of my assignment for presentation. Here we consolidated encryption time, energy consumption, and security strength into a chart. Starting with Ascon 128, it was the strongest and all-around performer, combining speed and efficiency with solid cryptographic strength. ChaCha20 fell into a balanced middle ground, consuming more energy than Ascon, but excelling in situations that need constant uptime. SPEC was a lightweight in every sense, small, fast, but too weak in security to be used in critical applications. This makes it clear which protocols are practical for real-world IoT deployments. Moving to our research-based trade-off analysis, from RADA, we learned that Ascon 128 not only performs well, but is also optimized for constrained hardware, making it ideal for edge devices. Al-Hassan focused on ChaCha20 and showed how it balances CPU load and energy gain, reinforcing its usefulness for always-on devices. Henriques and Wernicke's 2017 study confirmed that hybrids AES plus RSA models are a best practice, providing strong security and optimal resource usage, with our key metrics being encryption time, energy in millijoules, and security strength in bits. Moving to our challenges and limitations. Now, we did run into several limitations during testing. First, the scope of our testing was fairly narrow. We focused on 5 algorithms across 3 wireless types and only 2 microcontroller boards. So while our insights are strong, they're not universally generalizable to all IoT devices. So we had to abandon our original plan to simulate with NS3 due to complexity in setup and configuration. Some limitations surfaced as well. Wokwi, our hardware simulator, had limited library support, so we had to manually implement encryption and decryption logic using C source code from GitHub, which added time and debugging challenges. Moving to our continued, just basically how we analyze symmetric and asymmetric encryption. We were really only able to test a few asymmetric algorithms, and most of the metrics we used were software-based, meaning hardware acceleration could change the real-world results, especially for AES, which is commonly supported natively on IoT chips. We also discovered limitations with ChaCha20 as implemented in PyCryptoDome and RFC 8439 and only supports 256-bit keys. There's no officially supported 128-bit version, which slightly skewed our symmetry in comparing it to other lightweight algorithms. Still, despite the imbalance, ChaCha20 consistently outperformed others in many relevant categories. Wrapping things up, symmetric algorithms are faster and more efficient overall, but asymmetric cryptography is crucial for security key exchange, Hybrid models combine both stand out as the best strategy for IoT applications. Ascon 128 delivered the best overall performance in terms of both speed and energy efficiency. Charger 20 comes in next, offering solid security with moderate energy needs. And Spec consistently comes in last. In terms of trade-off, symmetric options like Ascon are ideal for constrained IoT environments. They're lightweight, efficient, and secure enough for most applications. Basically use Ascon or ChaCha 20 where possible and implement hybrid encryption models to get the best of both worlds. And here's our references.